Welcome everyone to week 3 of the Womanium Global Quantum and AI program. It is amazing to see everyone's faces here, many new faces, many familiar faces from the past 2 weeks, from the past years. Today we will start 2 new chapters. We will enter the chapter of artificial intelligence this week, kicking off with a presentation on AI for climate today by Kalai Ramea, and on Friday with a talk on AI for materials discovery and a talk by NVIDIA on AI, quantum, and HPCs. Then this week we will start with advanced quantum algorithms, a comprehensive course consisting of 8 sessions with classic, and we will do 1 session a week, gradually proceeding into the topic. Also this week we will have a virtual lab tour by Oxford Quantum Circuits, and today we will introduce you to the key partners for the projects that we will have this summer, the Naval Nuclear Lab, Fraunhofer, and Classic. Excited to have you here, and Lindsay will kick off today's talk and introduce our speaker.
Good morning. We have our first AI speaker today for this program. Dr. Kalai Ramea is the co-founder and chief technology officer of Planette, where she leads the technical development of medium-range climate forecasting products. She's an accomplished interdisciplinary scientist working in the intersection of AI and sciences. Her doctoral studies focused on developing mathematical models for analyzing climate policies, specifically for the state of California. During her PhD, she was also chosen to participate in a competitive research fellowship program at the International Institute for Applied Systems Analysis in Austria, a renowned climate think tank contributing to annual climate action and IPCC reports. Prior to founding Planette, Dr. Ramea was at Xerox PARC, where she led a technical area focusing on the development and cutting-edge AI projects aimed at climate action and energy systems. Welcome.
Thank you so much, Lindsay and Marlou. As introduced, I'm Dr. Kalai Ramea. I work on the intersection of AI and climate. So for today, let me go over like a brief introduction of AI ML techniques. This will be fairly preliminary, so forgive me if this is something we already know, but we want to lay a good foundation before we talk about how to use these techniques for climate. So it's always good to go through these. And then the next one, we want to see how we can use some of these algorithms and on climate change related issues. So I will go through some focus areas that the people are adopting right now and some examples from others' work as well as my own work. And finally, about Planette, which is the company that we co-founded and I'm currently leading. So I'll briefly talk about that as well. And some ethical and fairness considerations when it comes to using AI techniques for climate. It may be different from what you have already seen for like image or language. So I will also go through that as well. And like, what are some next steps that you could do, take it forward from here. So I just want to put a disclaimer. This is not an exhaustive coverage. Like you can imagine, your creativity is the limit. So you can always use any kind of application with the things that you have done. But this is just a teaser for you to get started in this novel area. And obviously we need all kinds of people coming from different backgrounds. So don't think this is limited by whatever I'm showing right now. All right, so a quick definition of the things before we jump into some introductory material. So there are 3 terms that we alternatively use these days. Like artificial intelligence is a more broad term. By definition, what it means is like ability of any machine to imitate human intelligence. So that's like a broader umbrella that we are looking at. And in the past few years and decades, even like, machine learning has gathered a lot of momentum. It's like a subset of artificial intelligence. And the reason why it gathered a lot of momentum is because of the availability of this data. The big data revolution exploded and machine learning algorithms, became popular and mainstream in the last few years. And what that means is just like the ability to incorporate the data patterns into the machine and automatically learning from those things. And then within the last few years, even like a subset of machine learning called deep learning that exploded as well. So what this means is like, there's a specific type of algorithm that mimics human brain to incorporate intelligence into machine. So don't worry about the details now. I just wanted to show where these different terms lie. So you can actually like organize within your brain, like, this is what you're looking at. And don't get confused by these interchangeable terms that we use in many contexts that we use to denote artificial intelligence. All right, so let's look into what machine learning is. So simply stating, it can stem from like statistical techniques or algorithms even. And the main job of machine learning is to learn patterns from data, as I mentioned. And the reason being, like, it's going to allow systems to make predictions or decisions without explicitly telling them, like, one way to do that is like give a if task, like if then, like if this, do this. If you're looking at this image, like classify as that. Instead of doing that explicitly, you're actually letting the algorithm decide it for themselves. Now, that's what it means in the general terms. So if you want to look at different types of machine learning, the most common one that you might have come across is supervised machine learning. I will go through in detail what these means, but just know there are like three major types. One is supervised, and another is unsupervised, and another is reinforcement. And I found this particular image like very cute to understand what it means. So basically, a supervised machine learning is like you're telling the algorithm what exactly they're looking at. So in this case, the robot is looking at like something like a cube, and then you're just telling, oh, your cube has 6 sides that are square. So it knows what it's looking at. And then the next time it sees a cube, it can decide that it is a cube. Now, unsupervised is it doesn't know what it's looking at. Like you're not giving the labels explicitly, but you have given the robot like a group of several blocks of different shapes, and it's learning to distinguish by itself. So that's what it generally means for to do unsupervised learning. And finally, reinforcement learning. This is where you see a lot of robotics applications in. It's where you teach an agent on how to assign a different shape to a different task. So in this case, the robot is trying to fit this cylindrical object into this round hole, and then like it's trying to decide, oh, does this work or does this work? If that works, then it gets a reward, and so on. So thinking about these things, like this is where most of the machine learning applications are in. Like you have a label. This is called a target or a label. You tell the robot, like, this is the label and this is the data, fit this label onto the data. And in unsupervised, you don't give a label. You just say, like, this is the data, do what you can. And then these will like segregate into different groups. And in this case, you explicitly teach a robot, like, like if you see this particular shape, if you can fit this, then you get a reward. So that's what it is. And so if you take supervised learning, there are two major kinds of problems that you can solve. One is regression and another is classification. Now, regression is where you have different data sets and you fit the data set in there. In classification, you classify the data, group the data into different categories even. Now, the difference between the unsupervised and supervised is like here you know the label. Like you tell them, like, if this looks like a plus, put it in this bucket. If this looks like a circle, put it in this bucket. In this regression, you can see like this is the data, like what is the best curve that can fit it. So, if you get another data point, like where can you fit this in this line? So some examples of supervised learning is like, say, for example, you're predicting a house price in a neighborhood. You can take the square footage, like family size, or like the school district and all what you can, like you take all those variables and then you say this is the median house price. And then if you take the similar footage of in another house that you're about to sell in the neighborhood, you can use that model to predict what might be the house price in that neighborhood. And that's a simple problem. Like anyone who started with regression, they will start with something like predicting the house price as like a simple example to get started. Another place related to climate that you can think is like estimate energy consumption. Similarly, like what kind of insulation you have, like how many people live in the house, what are their timings and all of that. And then you can assign certain energy consumption in there. And then you can estimate using a regression model and see, like, these are the criteria, this is the energy consumption of the house. Now, so classification, the most famous example that you have seen is like cat versus dog, where the model it looks at the image and then decides. This is where you use computer vision or like a simple logistic regression models. So basically, what the model sees is like it has two labels in this case. It sees like certain images labeled as cat and certain images labeled as dog. So it sees those patterns, it learns the patterns, and then when it has seen like like several thousands of images, and then you give a cat image or take a picture of your cat and show it to the model, and it will be able to say, hey, this is a cat. So it can do those kinds of tasks, or even different types of cars. Like it doesn't have to be one or two. Say you're like classifying different cars in your automotive factory. You can actually take pictures of those things, and then it should be able to like identify the different types, whether it's 10 or 15 even. And another famous example for classification is email spam detection, which is like a lot of email servers use. If some text looks like a spam, if some language looks like a spam, then it can assign that it is a spam, and then you get filtered. Now, the way they do is like they train different spam versus non-spam data. They assign labels for spam, then they assign labels for non-spam, and then they will train this model, and then automatically it should be able to like do at a fairly decent degree whether that email is a spam or not. So these are some simple regression and classification examples. Now, the other unsupervised learning, like I mentioned, the robot, like it decides which groups they are. That's exactly it is for the most part of unsupervised learning. The famous algorithm that they use is k-means clustering. K is the number of clusters, and then they use like, how to classify these clusters in there. The common examples of those is like, it's used in market research, like how do you do customer group segmentation? Now, this is a problem where you cannot do supervised. I mean, you can do if you have data, but most of the time you don't have the data. So you just are getting the customer details, but you don't know like how do they classify into different groups. So you have to let the model decide first, like, are there similar patterns between the data sets that you see? Someone living in, I don't know, like in Austria with this demographic, what do they buy? And then someone living in California with this demographic, like, what do they buy? And if there is a relationship between those things. So there are different, like more simplistic to advanced ways of doing this segmentation. And this is where when you don't have labels, and if you want some labels, like this is where unsupervised learning could help. Another famous example is like document clustering, where, for example, like you are collecting several kinds of news articles, and you don't have time or capacity to label each of them. Can you read the documents and like let them cluster among themselves? There are some topic clustering algorithms that you can use. So it will read the keywords, and then it will cluster them into different topics like crime or like breaking news, whatever topics that you want. Like it can classify into themselves, and then you read them, and then you can give the labels later if you want. And the most important application of this is anomaly detection. Now, this is where like you want to see if that something is deviating from the norm. So you can do this with, when you classify these groups, you can see if something is not fitting in, right? And then you plot it, like if something is out of the normal. You can even do it in regression, but this is where you know the patterns, how it's grouping up. Is there a deviation from that pattern, the normal? Okay. Now, reinforcement learning, this is a fun algorithm. I like this image very much because it kind of like, you're training the robot like you're training a dog. So say if you're trying to teach your dog some new tricks, like what are the things that you'll do? In this case, they're teaching the dog fetch, right? So, you show the object, and then you throw that for the dog to fetch. Now, the dog will go fetch it, and the moment it does it, you give a reward. It's a treat. You're doing the same thing to the algorithm in this case. You're teaching the robot to do certain things, like whether it's like, if your Roomba navigating your room. If it's hitting a wall, then it's not going to get a reward. It's maybe a penalty, like, do not do that. But if it's like navigating correctly, like it's internally getting the reward, like, yeah, this is a good sign. This is a good sign. And that is how you train a reinforcement learning algorithm. And there are several places like OpenAI Gym where you can go and like train certain agents for that. And these stacks are very, like I said, robotics is a huge example. And there are several other agents like social agents that you have been using for different policy examples. That if you want to optimize a certain policy for a certain organization, people use these things. Comparatively, this is not the most commonly used. When you rank them, it will be like supervised, unsupervised, and reinforcement learning. All right, so how do you train the model? So this is like a very basic pipeline. Obviously, like as you go into more details of machine learning algorithms, you will find a lot of ways to fine tune this. So say you get a training data, whether it's any model, say it's a supervised model. So you train the machine learning algorithm and then you get the model. Now, while training it, you also evaluate whether the model is doing good or not. So you actually set out a validation data. So when you get the training data, you separate them into like 60% of the data is for training, 20% is for validation, and then another 20% is for prediction. Now, the reason why you split this, because you don't want data leakage problems. Like whatever you train the data with, it should be contained in itself. And then whatever you're testing it should be out of the training data so that you know the model actually works when it hasn't seen the data that it has trained. So that way it's more robust. So you evaluate the model first and then get the final model. And then you have this data is testing data or prediction data, and then you test the model and then you predict it. Now, this is a very simple workflow. For the most part, this is what you need to know to do machine learning. You can take off-the-shelf algorithms, train the data on it, and then you can predict it, right? So now I'm going to switch gears to climate because we are going to talk AI for climate. Marlou, are we taking any questions at this point, or is it towards the end?
Let's discuss the questions at the end. Thank you.
Okay, thank you. All right, so why climate action now? It's not, it's almost like obvious, like we are in a climate emergency. And I want to give like a technical reason why we are in a climate emergency. What you're seeing is a daily sea surface temperature. So you can see these are all the other years since 1979. And there was one anomaly in 2016. And then 2023 is when like scientists started freaking out. Like what is happening to sea surface temperatures? Now, if 2023 is bad, look at where 2024 is. So what this means, ocean is the indicator of all the things climate, right? So it's like almost Earth's hard drive. So whatever going on in the climate, it's getting absorbed by the ocean first. So this is an indicator of what's going to come. If we are at this stage, like the Earth has never seen this kind of temperature before, at least in the recorded history. So what does this mean to us when you're living in a climate emergency? So this is where we need all hands on deck. This is a complex challenge because we are solving the Earth system challenge. So that means we need all hands on deck. Now, AI is poised in a right position right now. It's making huge strides in image as well as in natural language. So the reason why several AI scientists and climate scientists have come together is like, how can AI help this climate emergency and how can we contribute to climate action? Now, climate data sets are huge. They are in the order of terabytes to petabytes. And traditionally, climate scientists have had a hard time managing this. They have run traditional Earth system models that may take like months to even like, several months to run. And this is where, AI can have a huge impact in terms of processing this data and helping this. And climate is a complex systems problem. Like, it's not like you solve one thing and then it gets done. It has several interconnections and it requires advanced solutions. So we need to think about solutions coming from different aspects, like merging machine learning and traditional models and so on. So we definitely need all of that. And like I mentioned, like AI has made significant advances in the recently history, especially in image and natural language. So it can handle a lot of data. And that's a good news for climate science, because most of the time, like AI scientists feel like, oh, we don't have that much data. But in climate science, that's the opposite problem. Their data sets are huge. So we definitely can use AI for this particular problem. And the most important thing is we have high performance computing now, which wasn't accessible before. So as you know, like NVIDIA has been making news with the news about GPUs, but we are exactly using the GPUs and high performance computing to process these climate data better than before. Now I want to focus on different areas that I've bucketed by the way I see it, that people have been using for climate action. One is computer vision, natural language processing, data-driven optimization, and finally, physics-informed machine learning. So I'm going to go through some use cases. Like I said, it's not the exhaustive use case, but some of them just to give a teaser on how people are using it. For example, if you take computer vision, this is any AI algorithm that can process vast amounts of like image or remote sensing data. When I say remote sensing, it's satellite data. So they are huge in number, and it's almost like they're inundated with satellite data in the traditional domains, like whether it's remote sensing or climate. And the most common application that's been used is classification or segmentation. Now, classification is like I mentioned, like classifying whether this is like a or B. Segmentation is you draw a bound around that object. If you, in this case, like you're looking at this like person, you're segmenting this person, you're segmenting this car. So this is segmentation. So this is the most common application that's been used, like classification or segmentation. And there are new satellites getting launched almost every day. And these are very high resolution satellites. They're almost like fancy drones that are circling around our Earth. So they're collecting very high quality data. And like I said, the possibilities are endless with this information available. So I'll go through some examples, like forest monitoring is one aspect. For example, companies like Pachama, they use remote sensing and AI to look at how forests evolve over time. As you know, like several companies are buying carbon credits in terms of forests and land, but they would want to know like what is happening to the forests over time. Say if they commit this kind of carbon credits for the forest, then they may want to monitor whether it's getting deforested or are they getting affected by wildfires. So this is a huge aspect where Amazonian forests are monitoring their forests, because you cannot do that manually. You cannot have that manually. There are only certain things that you can do by satellites. Traditionally, remote sensing scientists have been like drawing by hand, and then like classifying them by indices and so on. Now AI algorithms have come up and said like, oh, this is computer vision. Like we are segmenting this forest area, we are segmenting this like wildfire burned area and so on. So that has been super helpful in this case. And secondly, coral reef monitoring. As you may have seen in the news, especially with ocean's temperature rising, coral reefs are dying, unfortunately. Several governments like Australia, they are putting in a lot of effort to restore them. But the first step is just understanding what is happening to these coral reefs. So traditionally, you have these like scuba divers going and like taking pictures and then coming back to the lab and then like identifying what's wrong with them picture by picture. But now if you train an AI algorithm, say if you can like train the diseases of coral reefs, which one is getting bleached and so on, or which stage of bleaching it is in, and what kind of intervention that we need to do, it's able to like automatically detect those things. So it reduces a lot of time after these pictures are taken by like manually. So this is being intensively done right now. Another place is air quality monitoring. This played an interesting role during COVID, for example, because when we all went into lockdown, that's when we were able to see like how much the air quality improved. And when people saw the up and down in there, you could see a vast difference. Like there was an image circulating like a before and after of lockdowns. Anyhow, the way we can use this is for several reasons. One is like the particulate matter itself. It's not exactly related to climate, but it's related to environment. And another is like due to wildfires, like what kind of air quality you can have due to wildfires. This is where, again, the segmentation algorithm could help, just assigning like this is of like a poor quality and which areas are affected and so on. Now, the most important or like popular application that we have been seeing is this precision agriculture. So there were several things that's been happening here. One is like yield monitoring or crop monitoring, like what is happening to the crop. You can fly a drone like this, and instead of the farmer going crop by crop and monitoring it, they can actually see whether the field is ready for the yield or which one is affected by pesticides. You can even take a picture of the crop, and then you can say like what kind of plant disease it has and what are the medications that need to have. And also water management, like there are several satellites up in the sky that manages soil moisture of these farmlands. So they can actually see through the hyperspectral data or multispectral data and see like the level of water stored in these lands, and then see how much they need to be irrigated, for example. So there's so many things that have happened, and this has a term called precision agriculture. And as we go into the new normal of climate change, food insecurity is going to become a huge problem. What this means is like the way we have done agriculture is not going to be the same as before. So we need different methods to adapt to this new climate normal. That means we need to know what kind of new crops that we need to grow, when to grow, and also like if this is the right time to grow, or what is happening to the water levels and so on. So with this, yeah, I will move on to the next one, which is data-driven analytics and optimization. And this is where some of the reinforcement learning that I talked about comes into picture. So take this example, smart grid. What smart grid means is they have this centralized grid that manages everything in the neighborhood. For example, you have the cities and offices with their residential energy, lighting and all of that. Sorry, like the company energy. And then you have the residential energy coming from smartphones. You have solar panels in there. You may have electric cars in there, the charging for that. And you also have these wind power plants, solar power plants, and hydro, and other kinds of factories also happening in there. And also you have distribution systems and everything. How will you optimize this so you can make the best use of energy? Now that's like a huge problem, right? You have so many attributes to consider, and there are so many pathways to consider. Now this is where the optimization and in terms like data-driven AI could help. Now the field of optimization is old. People have been using that for several years, but what's new is incorporating data-driven optimization in there. That's where your reinforcement learning algorithm comes. Like for example, you can teach the thermostat in your smart homes, like when to heat up, when to cool up, and like suggest like seasonal savings that you have seen on Nest, or even like what kind of price that you need to decide for electric charging. If you think like people are charging at the same time and you want to reduce the load on the grid, like you can introduce some pricing incentives so that they can charge in the nighttime, for example. So there's so many decisions that you could make, and this is a very interesting space to be. And currently with, for example, the IoT, the Internet of Things, which means just sensors that are connected to different devices, they bring a wealth of data that you can optimize. Say if there are sensors in the car, sensors in the house, and sensors in so many wind and solar, like how can you bring all of that together and how can you optimize it? This is again a data deluge problem, like how do you find anomalies in there? There's so many things that you could look into this area. And language and AI. So this is, language and climate action. This is an interesting space because traditionally when you think about climate and its applications, language is not the most involved application so far. But then with the recent advances in generative AI models and the language models in OpenAI, people have been starting to experiment with this. So for example, in my introduction, they would have mentioned that, I worked on IPCC reports. Like if people don't know what IPCC reports are, they're Intergovernmental Panel of Climate Change. It's a mouthful, and they produce these several pages of reports every year or every few years, showing where the Earth is at in terms of climate and where the countries are at in terms of climate action, right? If you think about it, this is the most important document that humanity should read, but it's boring and it's long. Like if you want to translate this to lay people, I don't think if anyone would sit around and read 500 pages. So one of the scientists, they made this chat IPCC. So what this means is like you can pretty much like chat to the IPCC report and find out like, hey, what's going to happen, for example, to India in 2020, and it should be able to tell A, B, and C, and this is what Indian government is doing for that. That is super helpful, and it's teaches public on like what is happening in the scientific world to the real world. So I see a lot of advances like this in the climate space. And there's just one example, like I said, like creativity is your limit. Think about how we can take some of these things to the climate world, like these language models to the climate world. All right, now we go into a little bit of sophisticated models. It's called physics-informed machine learning. So as I mentioned, the machine learning, the one I mentioned, is purely data-driven so far. So you might have seen like input data, train the machine learning model, test the model on output data, testing data, and then you get the prediction. Now, in the last few years, there has been a rise in physics-informed machine learning model. What this means is it's adding physics constraint so that it learns about the reality real world a much better way than just learning from data. I'll give a simple example to understand what this is. Say you have an apple tree where an apple falls from a tree, right? Now you can pretty much fit a machine learning model to understand if an apple falls from the tree, where will it fall? So drop an apple from that tree, like 10,000 times, and you can fit any line in there. Like you can fit a regression model and then say like, okay, if that apple falls from this tree, it will fall anywhere here. Now this is a machine learning model. Okay, so that will work for this tree. Now, say you have another tree somewhere else, say on a hill somewhere. Now, if an apple falls from there, will this model that you have fit here, will this work on this model? It may or may not. So it may even work in reverse. Like say, for example, this is on a hill, and then if the apple falls from the tree, it can give a negative direction even, which is not consistent at all. Now you introduce a simple concept called gravity in there. Say the final position of the apple is always going to be lower than the initial position. And immediately it generalizes to all trees, whether it's on a flat valley or it's on a hill. Now, this is what physics-informed machine learning is, in essence. Like you're including a kind of physics concept as a constraint, or as a different architectural enhancement, which it's a more sophisticated way of doing this. And then you would immediately generalize. So the results you're getting is much more consistent with the real world. So in this case, like you don't have to train the model again on this new data, which is what you would normally do if you're just doing a data-driven model. You train on this model, you got a machine learning model, and there's like, oh, I got another data, I have to train 10,000 times on this. And then I have another tree, I have to train 10,000 times on another tree. So instead of doing that, you immediately generalize on all the trees in that neighborhood or in other neighborhoods just by this method. Now, the people have been using physics-informed machine learning for climate action, specifically for climate models. So if you take climate models, the way they're doing this is like, you take each grid, like a spatial grid on climate data, and then you resolve several physics equations in that entire sphere. And this includes, like hundreds of thousands of equations that you're resolving at each grid, and it will take a long time to run these models. And it has several teleconnections. So for example, if you do something in the Pacific Ocean, it affects around the globe, like in Africa. So this has several teleconnections, which all need to be captured in this case. And like I said, and even if you can imagine, like resolving each equation on this grid, it takes weeks to months. So even if you have a large number of data, it's impossible to generate large scenarios with machine learning model. So you need to have some kind of shortcuts to make it more manageable to run. Otherwise, you'll be just training the data all the time. So weather forecasting, climate forecasting, and we all use machine learning, physics-informed machine learning models in this case. Now, one use case that I want to give, just take it with me. It might be a little bit more advanced, but roll it with me for now. We developed this model called AI Beto. It's a hybrid AI model to capture the effects of cloud, on circulation and regional climate patterns. So let's talk about clouds for a moment. Like if you look up the sky on any day, you will see two types of clouds. One is this fluffy clouds, it's called stratocumulus clouds. And another is these breezy clouds called cirrus clouds. Now, these are good for climate change. Now, what do I mean by this? It is in the lower atmosphere, so it reflects sunlight. So it's good for cooling the planet. Now, these things, though they do look beautiful, they are bad for climate. They are found in the upper atmosphere. What this means, they absorb sunlight. So almost like a glass, they absorb sunlight and it induces warming. So they also, like if you think about clouds, they play a huge role in how they affect climate. So forget about this part for now, but these are the things clouds impact: the surface temperature, precipitation, rainfall, the monsoon season, the position of the jets are these atmospheric vents, and these are other climate specific terms that they affect. So if you change anything in the cloud, it's going to have a response in the climate. So that's all you need to understand from this. Now, one thing that has happened recently, and also it's related to the ocean temperature that you saw earlier. This is an image from a satellite taken off shipwrecks. So these are where ships went. So you can see the cloud lines over there. So what has happened is ships emit the pollutants or sulfates, aerosols. They go into the atmosphere and then they form these cloud streaks, and they were reflecting the sunlight. So it was cooling the earth. So recently, there has been a lot of policies on shipping where they reduce, that they decarbonize the marine vessels, which means like you cannot have sulfates in there. So basically, this is to reduce air pollution, right? So what has happened is these streaks have disappeared, and this is the reason, or at least one of the reasons, why we started seeing this unusual high in the ocean temperatures. Now, this is a problem when we are going to do climate action without reducing CO2. If we reduce other pollutants, we are going to be in a hard time. So this is one way of, we understood like, okay, the shipwrecks are unintendedly, accidentally like helping the planet. So then there are like other people looking at like, can we do it intentionally? And now this is an area of climate intervention that some of the research groups are looking at, like how can we brighten these clouds, like stratocumulus clouds, and stabilize climate or avoid tipping points. But as you can imagine, like, this is a complex problem and also like somewhat scary problem. Like if you brighten certain areas, as I mentioned, the Earth is a teleconnected region. So if you brighten certain regions along the coast, what will happen to the other regions? Like, will it have a negative effect? So just to give an aspect, don't worry about the text, but the blue circles are all the tipping points in the climate. So what I mean by tipping point is like when this reaches, for example, take this example of West Antarctic ice sheet. If this melts, it leads to a feedback loop where you go to a point of no return. So what this means is like, if the West Antarctic ice sheet melts, I read that it leads to like several feet or meters of sea level rise all over the world. And it will go into a feedback loop, and it will be impossible to stop climate change at that point, like climate related impacts at that point. And similarly, the biodiversity collapse in Amazon and the permafrost that you might have all heard of and so on. So there are ways we're looking at like, how can we use these climate intervention strategies in the way that it prevents these tipping points. At the same time, it doesn't impact the other regions in the world. So this is a project that we did for the US Department of Defense, DARPA, where we developed this model to understand how we can train cloud properties, and then like so that we can avoid these tipping points, and then we can set certain levels in there. So this project, this project available AIB.readthedocs.io, like feel free to go through that. This is an open source project. Like you can see the models that we implemented in here, which I'm not going through in detail, and how it's being used right now. All right, so finally, I'll drop a bit about Planette, and then I'll wrap up for questions. So this is our new venture. So I quit my job at Palo Alto Research Center or Park, and then founded this company. The reason we founded this because, there are so many companies that's doing weather scale stuff, like which is like, 0 to 14 days. There's some AI algorithms pushing this to like 3 weeks or 21 days. So this is a huge space and people are doing awesome work at it. And then there's a huge gap. And then you see all these like climate related forecasts that's going to happen, what's going to happen in the next 30 to 100 years, which is where, the Copernicus or NSF or NOAA, they're all working on this time scale. Now, my co-founder and I realized like there's nothing happening in this monthly, quarter, annual, or multi-year. Now, this is where a lot of decisions are made. So if you're a business thinking about like what should I strategize for the next year, you need to know what's going to happen to the wildfire risk or flood risk, or it's going to be a heat wave, so I can like stock up properly. There's so many decisions one could make in this time frame. So that's where we decided to focus, and we now have a company that produces these, we call medium range or gap forecasts or bridge forecasts. So that's what we do. So yeah, feel free to go to the website planette.ai to look more into what we do. So this is a final section. I'll wrap up with this. So there's always some ethics, bias, and fairness considerations while using AI, even for climate, right? So we typically do not deal with personal or demographic data. We are not doing like facial detection or anything, but we need to be aware of the ethical consideration of regions. So what I mean by this is a lot of the data availability is generally poor in global south countries. So be aware that whatever model you train on global north, which is where it's supposedly data rich, you cannot just transfer to global south without any considerations for the regional factors. Even the several climate models that we use, it's initialized for global north and not optimized for global south. So this is something we take into consideration while we are training our models. And also like be aware of energy expenditure. Like, I mean, this is a thing, especially after the generative AI models, like language models, the AI model itself is extracting a lot of energy, almost can be compared to countries. So even though like it's helping the climate models in a way, like, we are transferring one kind of model to another. In this case, like if you're training on climate science models, which is like huge in itself, we are saving energy. But be aware of energy expenditure if you're training on other language models or computer vision models. Like it cannot be like you're doing this for climate, but then you're also like affecting climate. And this is the most important thing, collaborate with domain experts. So the thing that the disappointing way that I've seen like several people go about and do this is like they think AI can solve all things. They just go take a data and then they'll just fit a model and then they'll just show the results. But I cannot stress the importance of like incorporating domain experts. They can interpret the results and they can even say why you're getting the results that you're getting, or if you're getting it for the wrong reason. So there's always this interpretability and trustworthy models that you should develop. And in my experience, my co-founder is a climate scientist. So we talk all the time to come up with the best models. And also like I've understood many times, like their expertise has helped the AI modeling in a way, like especially when you're incorporating physics constraints and such. So we come up with like novel architectures all the time. So always work with domain experts, reach out to them, and they're happy to look into in these problems. So I'll leave with this thought. Climate change is a problem of our lifetimes. As you know, like the time to action is now or yesterday. It has so we need to do all hands on everything, and all hands on deck is needed to do that. Now, with unprecedented advances, the opportunities are there. So let's be creative, collaborate, and solve some exciting problems. And there are some interesting links. This Climate Change.ai is an organization that brings in folks from climate and AI together. And currently they have a summer school for AI folks to learn more about climate. I would highly recommend that. And then some of the competitions like Driven Data, even Kaggle has many climate and AI related competitions. So we can look into that. So yeah, that's where it is. And thank you so much for having me, and take some questions from here.
Thank you so much for that talk. It's so informative and such an important topic for all of us to be paying attention to. And I love just your ideas and innovation that you're bringing to all of this. We do have a lot of questions. I know there's a few with quantum and the relationship with quantum computing and machine learning. I'll get to those in just a second because there was a few of them there, but I did want to start with a question in relation to where did it go? This is from Juliana from Italy, who's asking, does the AI veto model consider orography?
Not yet.
Orography,
not yet. Yeah. So because we are dealing with atmosphere at this point. So yeah, like I said, that was a research project. So you can obviously include land use orography as you go on, like to make it better. That was like a 1-year project that we worked on, and I moved on from that project after that. So definitely there are ways to improve from where we left off from there.
Great. And Natasha Val from the UK asks, how can we improve data collection in Global South to support the AI modeling?
Yeah, that's a great question. I know like there are several foundations that are working on that right now. The main thing that I've done is like just give, and I'm talking about this from the climate science point of view, they're given compute hours to Africa, for example, so they can run their own version of climate models. So that's one way to do that. And also there are several, like Gates Foundation has done a lot of like, data collection in there. And then there are satellites being launched specifically for Global South countries. So it is happening. But again, like we need money flowing through, I guess, like that is the only thing that's stopping from there. So that's beyond my expertise on how to gather momentum in the financial space to fund them.
Right. Absolutely. And Yara 305 from US and Brazil says, that's amazing that you started this adventure as a co-founder and CTO that benefits the Earth. She asks, how did you come up with the strategies to have a competitive advantage and research the market that you're in? And did you use AI for that or reach out to a network to help?
No, I'll ask that last question. No, we didn't use AI for that. So I think that the idea itself, like, we were looking into what was missing at this point. So we started with the long-term climate risk because, we were working on climate-related risks first. And then we were like, we talked to the customers. And then you're like, oh, would you want to know like what's going to happen like 10 years from now, 30 years from now? They were like, we don't care. Like, we know it's going to be bad, but what matters to the business is the next few months or years. So because they make decisions in that time frame. And on, like people were talking about like that they don't find the data in that time frame. So we did a lot of research, like secondary research and primary research in that space, and found that either people just interpolate the data, like historic data, and with the climate change, the unprecedented extreme weather events are happening more and more, and they're having a problem with that. So it's more in-person market research. Like there's no way around it. Like we talk to people, it's not AI. So we spoke to people and like time and again confirmed that this is a problem that they have. Again, like, we are both nerds coming from technical space. So the whole business side is new to us. So we learned a lot through that process. So we are happy about the journey that we have done so far and doing all of this.
That's great. Yeah, absolutely. Finding that problem that needs to be solved. It sounds like you took that route. Arshit from India asks, how exactly are physics rules introduced to the machine learning model in physics-informed machine learning?
Yeah, like I said, one easy way to introduce is through constraints and loss functions. So in the example that I gave, like gravity is a simple constraint that you introduce, like, the initial position should always be higher than the final position. So it's a kind of constraint that you can simply introduce. And if you think about the climate model, there are several other physics equations that you can do about, like, the energy conservation, like moisture budget, like there's so many advanced concepts that climate scientists use. So we translate them to constraints, and then we can use them in the model itself. So when it trains for every epoch, it will learn that, like, in addition to the model laws, it will learn the constraint laws and it will add up together. So that's how it makes it consistent.
Gotcha. So, and this next question from Ayana in India is kind of a mix of understanding that as well as some of the job prospects and everything. She asks, what are some companies working with machine learning and AI for climate action, in particular doing physics-informed machine learning? And she'd like you to tell us a little bit more about the job prospects.
Yeah, so I mean, like I mentioned, like if you look at all the weather companies that I posted here in our Planette page, yeah, there are so many companies in the space coming up right now. I haven't even put the exhaustive list. Like the weather companies are just exploding at the space. So and then like in the in-between space, like obviously we are doing this, and there's another company also doing this. So those are the two forecasting companies. If you go to a website like Climate Base or Climate People, that's a really interesting resource because they actually like list down all the job prospects in this. Like this is mainly for like people who are moving to climate tech. So there are specific websites for that as well. So yeah, I think it's Climate Base, Climate People, Terra.do. It's another.
Great. Yeah, it's definitely a growing field. One last question, because there was quite a few questions about quantum computing. If you could just touch on any of the areas that you are aware of that machine learning, AI, and quantum computing may be forecasted and being used in climate solutions.
So I'm a noob at quantum, so I'll try to best answer that. So I read a recent paper on quantum computing where one of the major advantages of that is the speed up that it's possibly doing, and also the way that's using energy. So I believe that might be the next frontier. I'm not sure. I'm speculating at this point, like because the biggest challenge with AI is just the energy part of it. Like it has been like an Achilles horn, like but for that. So that is the place where quantum could help if we develop hardware in the right way, if we develop algorithms in the right way.
Yeah, absolutely. Still more to come on that topic for sure. Well, I want to thank you for sharing your valuable insights with us today. Your expertise at the intersection of AI and climate science has provided us with a fascinating glimpse into the future. And your presentation is an introduction for our participants so they can continue learning about AI and potentially how quantum computing can work to resolve these complex problems. So we greatly appreciate your time and your passion for driving innovation. And thank you so much for joining us today.
Yeah, thank you. Bye.
A big applause to Dr. Kalai Ramea from Planette AI. Fantastic talk on AI for climate. And this might give you ideas for your projects at the end of this program. Thank you, Kalai. I will share 1 minute where we stand in the program with all of you before we proceed into the introduction to key partners. So we just started week 3 of the program. It means that week 1 is behind us, where we get an introduction to quantum computing and programming. Everyone is still working on the exercises. You can finish them till June 23rd in 1 week. Last week, we had an introduction to quantum computing hardware, and we focused on quantum annealing. Week 3, we are starting with advanced quantum algorithms on Wednesday. Today, artificial intelligence, and also continued on Friday. And next week, quantum machine learning. And all of this will lead to the Womanium Quantum and AI Industry Project. The Advanced Quantum Algorithms module prepares you for that. The AI module prepares you for that. The Quantum Machine Learning module prepares you for that. And today you will learn more about how these industry projects work, how the Womanium Quantum Solutions Launchpad works,